Hello all, I welcome you all to the ninth lecture of this course E690 ATM. The last time we met, we spoke about some very important aspects. We started to discuss about electrons in periodic lattice, and we came up with some expressions for the density of states in one-dimensional crystal, two-dimensional crystal, and three-dimensional crystal and such. And we saw that there are only discrete number of states in which the electron can reside in a crystal, and number of k states, number of the electron wave functions depends upon the number of unit cells it has. So even for a free electron or nearly free electron in a crystal, you cannot have continuous density of states. That is discrete. In 1D, the density of states diverges at low energies, particularly at E tending to 0. You have infinitely large density of states, and it vanishes as it goes to higher energies. In 2D, you have a constant density of states. In 3D, you have a square root dependence. This is what we saw. Finally, we derived the Fermi level value Kf for, let's say, for a simple example of gold, and came to this conclusion that the electron wave vector at the Fermi level is the topmost energy level, which is filled at 0 Kelvin. We have still not talked about occupation statistics, which we'll talk later on. But at this point, let's say that we only take Pauli's exclusion, which tells you that no two electrons can have the same energy and having all the quantum numbers the same, particularly the spin. Right? We found that the wave vector at the Fermi level matches with the wavelengths of interatomic distance. Right? So you are very close to the Brillouin zone, or very close to the first reciprocal lattice vector. So here if it is 0, we found that the Kf lies almost similar to the value in red. So your Kf wave vector looks somewhat like this. We also spoke about reduced zones and such that any electron whose wave vector is larger than the first Brillouin zone can always be represented by a value inside the Brillouin zone. You call what is called as folding back. Right? So this guy you can represent somewhere here. Right? So this was the short recap on what we had last time. So today what we will do is we will start to look more closely at what happens if we have an electron in the periodic lattice. So previously we spoke about how do we treat a periodic potential and such. We saw that you start to have electron wave functions which look like block wave functions. But today we will take a little bit different approach. We will use the perturbation theory and show that what sort of interaction or scattering does the periodic lattice does to an electron wave. So here the easiest thing to imagine is you have a periodic potential like this. So like what we show here, we have a periodic potential, and assume that the potential is not too large. Okay, so something we have here, it has a periodicity of the lattice constant R, as we discussed previously, and assume that you have on this sample an electron wave is incident, right, with the k, with the wave vector k denoted as psi k. And once it is incident, obviously we can expect it to be scattered from this particular potential, right? And we assume that the scattered potential is psi k prime. Okay, we will talk about the relationship between the two, what are its conditions when such a situation happens, right? So how do we deal with this? We use what is called as the perturbation theory, which tells us that nothing much changes to a larger extent. Okay, so let's assume first of all a free electron, H naught is the Hamiltonian without the perturbing potential, right? So basically it's a free electron with let's say there is no lattice, there is no potential, the electron is going free, and we know the solutions. It's a plane wave, right? So H naught is the Hamiltonian, and psi k is the free electron wave vector, sorry, wave function. Ek is its energy, and we know its dispersion. It goes as h square k square by 2m, right? So this is the standard Schrodinger's equation that we know very well about, right? Now, what is the assumption that we make is, when you introduce a lattice with such periodicity, obviously it is going to change the Hamiltonian, right? So your Hamiltonian is written as minus h bar square by 2m del square plus v. And it is this v which is what is changing. Initially, if we take the v to be 0, we get our free electron model. Now, instead of that, we have this v which is periodic as given here. So what we do is, if this v is small, right? So we are going to express this as, this is h, sorry, this is total h. We are going to express this total h as h equal to h naught, which is just this part, plus something which is written as lambda h prime, and h prime is small, okay, something which is small. When we express the Hamiltonian like this, then we express the solutions psi k, the solution to this Hamiltonian, to also in power series. This is what is typically done in any mathematical function. The expansion by Taylor series and all these things are are examples of this power series. You can always, so basically it has infinite solutions, I mean infinite terms, and you can always terminate it at some point saying the other things are small, negligibly small. What it means is, we always get, that is, the solution of an electron in periodic lattice looks almost similar to the solution of the electron in a free space, right? So basically this is what is the solution. So we write psi k as psi k naught, that is the solution of an electron in free space, plus some terms corresponding to the lambda. So lambda is this is the strength of this perturbation, right? So basically, to expand this, we will say it is psi k naught, the unperturbed wave vector, plus some lambda times psi k prime, psi k1, plus lambda square psi k2, plus so on further, right? If lambda is a small enough value, you can see that the higher powers will all go to 0, and only the first 2 to 3 terms will contribute. Right? So this is the conventional power series, and this is how perturbation expansions are written. If this is the Hamiltonian and if this is the wave vector, then you can always write the energies Ek once again in this power series expansion. You write it in this fashion. I use the summation here just to have a short notation expression. Okay. So now once again, the electron in the potential should satisfy the Schrodinger's equation, right? So let's go one by one. Let us see, for the perturbed Hamiltonian H, the new wave vector psi k. If we add the Hamiltonian on the psi k, we get these terms, right? So h naught is the unperturbed Hamiltonian plus lambda h prime, and the wave vector we have expressed by this summation. Similarly, on the right hand side, you have the energy Ek and psi k. Once again, there are these two terms, right? And remember, all of these things are polynomials, right? So whenever you have a polynomial, you equate, if you have two polynomials which are the same, then the coefficients of the corresponding powers should also be the same. So now let's look at each of these powers. Let us say lambda power 0, the 0th lambda power is the unperturbed Schrodinger's equation, which we already know. So our equation buildup is okay. Now let's look at the first power. So this is called as the 0th order perturbation. This is called as the first order perturbation. And this is second order. So what we have done, for the first order, I have taken all the terms which has just lambda. So on the left hand side, we have lambda h dash acting on psi k naught. So you get this h dash acting on psi k naught, plus you have h naught acting on psi k1. You get this term here. So these two on the left hand side. On the right hand side, you again will take only terms which has just lambda. right? So this will be your first order equation. Let us now look at just the first order equations, right? So, okay. So what we do is we take this first order equation and act on it. So this is the first order equation, and act on it from the left hand side some psi k naught. Okay. Similarly, we should do this for here also, psi k naught. We use the inner product multiplication using the Dirac notation. I suppose you all must be familiar now. So if we take, if I do this throughout the equation, let us split it in two ways. Let us once again do the left hand side separately and right hand side separately. If we do the left hand side separately, you get psi k naught acting on H dash is the perturbing Hamiltonian, right? So H dash is the additional, is the perturbance to the previously lying Hamiltonian, right? So we have H dash acting on psi k naught plus the other term H naught acting on psi k1 and psi k naught. So it's easy to see that this is something which we can easily resolve. So what we do is we move the Hamiltonian from this side to this side, and H naught being Hermitian should not change, right? So the first term I retain, the second term I move H naught to the left hand side, and H naught acting on psi k will give me Ek naught acting on psi k naught, right? And psi k naught, the Dirac inner product of psi k naught and psi k1 is obviously 0, right? Why? Psi k naught and psi k1 are the solutions of the unperturbed Hamiltonian, right? So basically this will go to 0. So what will remain on the left hand side is just this psi k naught H hash psi k naught. So on the right hand side, now let's do the same thing. I acted from the left psi k naught Ek psi k1. Once again, Ek is just a constant, so it comes out of this inner product space. You get psi k naught inner product psi k1 plus the second term is psi k naught Ek1 psi k naught, right? So basically this will again come out, and psi k naught inner product psi k naught in a normalized way should be equal to 1. So you get Ek1. So what we get is Ek1. Ek1 is the first order perturbation to the grounds, to the energy Ek, right? Is the Dirac bracket of psi k acting on H hat. H hat is the H prime is the perturbing Hamiltonian, right? So we will soon see what this equation actually means. What I just wanted to I'm just building the mathematical framework of this, and we will see what intuitively this expression means very soon. Okay. So this is the first order correction to the energy. Remember, we wrote the energy E to be, Ek to be Ek naught plus lambda Ek1 plus lambda square Ek2, right? So basically, if lambda is small, this should be the most dominant contribution change to this one, because lambda being small, this is small, and lambda square will go much smaller, and the lambda cube terms are obviously going to be negligible in comparison to this, right? So this is the most significant change that we are going to add, and that is this term. Lambda square Ek2 is the second order energy that we will soon see now. Okay. So if this is the first order change in energy, what is the change in perturbed state? Okay, so this is the first order correction to the first ground state or any state. Okay, it does not have to be particularly the ground state. It's just some state Ek. Now let's look at the wave function. Wave function we wrote as psi k plus a summation of the other powers of lambda, right? And we go back to our previous equation. This is the first order equation. I write that again here. H prime psi k naught plus H prime psi k1 is Ek naught. This is what we ground state energy, and Ek1 is what we just now calculated, right? So this is something that we know. Now what I do is I move things. So I move this to this side and I move this one to the other side. So I have H naught minus Ek naught psi k1 is equal to minus H prime minus Ek1 psi k naught. Right. So now I have to find psi k1. So psi k1, remember this psi k1 also is a wave vector in the Hilbert space, right? So what I mean, okay, so let me just give you a brief picture here. We will talk about this much further later on. So what I'm saying is, for example, let's take an infinite potential well. There are different energies, something like this, which goes to the power of n square, right? So this is E naught, E1, E2, E3, and you have its wave functions. First one is like this, second one it will be like this, the third one will take like this, and so on, right? So these are the wave vectors. This is, let's say, psi k3, this is, let's say, psi k1, and let's say this is psi k naught, correct? So these are the three different solutions, three different wave vectors, three different energies. What we are trying to do is, if I introduce to this system a small perturbation, like instead of the potential being 0 here, I have a potential block like this, something which will change, right? Now the question is, how will it change all the energy levels? How will it change all the psyches? And that is what we are trying to find out. So the first EK1 is like, I take any energy here, let's say E2. So I take E2, these are all E2 knots, right? So the actual E2 after the perturbation will be E2 naught plus lambda times some EK1 plus lambda square EK2 plus so on. And what is this first change? And this is what is we have calculated, right? So what we are saying is, this value, how much it is going to change, is the inner product space of psi k. We are talking about E2, energy 2, right? It's already what the wave function looks like this. I've called this psi k3. So it is psi k3 H dot H prime psi k3. So what I'm saying is, or what we currently found out is, I take the perturbing Hamiltonian, that is the potential here, act it on psi k3 and see what it results, because it's an operator acting on an eigen function will give you another eigen function, right? I take that eigen function and I do inner product of this. Let's say the result of this is some psi n, okay? Take this Hamiltonian, act on psi k3, and let's say it gives psi n. This term, what it gives is the overlap function of the original psi k3 with this psi n, what you got after the perturbation acted on this wave vector, correct? Now what typically happens in most of the time, okay, obviously it can give you some non-zero value. Most of the time what it does, this psi n will turn out to be one of the other existing wave function, existing eigenvectors, right? If it turns out to be, let's say, some existing eigenvector psi k4, it's obvious to see that this overlap will be 0, because we know all the eigenvectors, all the eigenfunctions are orthonormal, right? So mostly EK1, the first order energy correction to a small perturbation, will turn out to be 0. So this EK1 in most cases turns out to be 0. What it means, what we mean is, these energy levels do not largely change, do not undergo huge variances because of this small potential. This is something that you all always expect, right? So this is fine. But why I went through all these things is to give you a feel for what does this bracket notation tell you. This bracket only tells us that H prime acting on psi k naught should give you a wave vector and its overlap with psi k. So this is basically, if I write, it is psi k naught star psi n. Psi n is this one, right? Psi 1 and of r. dr. This is called the overlap integral. This is what this guy means. Okay. All right. So now that we have cleared some background, now let's go to the actual solution. Oops. Okay. So now we are trying to find, we found the energy. Now we are trying to find what should be psi k, right? For doing that, I have split psi k1 as summation of some. So basically this psi k1 is the perturbed wave function, right? Addition to the perturbed wave function. So how can I write that? I can write psi k1 as a summation of older unperturbed wave vectors, CL psi L naught. So these are all unperturbed wave vectors. Remember, the unperturbed wave vectors are a basis of this Hilbert space. So I can always write any wave vector as a summation of this unperturbed wave vector. So I write psi k1 as as Fourier series expansion of this unperturbed psi L naughts, psi k naughts. So I got the previous equation. I just rewrote the previous equation, whatever that we have here. I wrote it back. Now I substitute psi k1 as the summation. If I have the summation, these Hamiltonians can go inside, right? So h naught minus ek acting on CL psi L. So basically these are all knots. Okay, I should write knots here. Again, not G. Okay, so H acting on psi L will give me EL, correct? So H naught psi L gave me EL psi L minus EK psi L. This is standard, correct? And CL can be constant, again is taken out. And obviously this summation will turn out to be 0 if L is equal to K. So from summation to all L's, I have just made L not equal to K. CL EL naught minus EK psi L naught, correct? Now this is what we found from the left hand side. On the right hand side, we have minus H prime minus EK1 psi K naught, right? Now once again, as we did previously, I do an inner product with some eigenfunction psi m naught, once again from unperturbed wave vectors. Okay, these are all, whenever I have a knot, I have an unperturbed wave vector. This would again be a knot. So when I have something like this, as we did previously, psi m goes inside, and you will see that there is only in this summation, all the other terms will be will be 0. Only thing which will survive is what, when L is equal to M, right? Because psi m psi L, psi m inner product psi L will be non-zero only for L equal to M. So under such situations, this L equal to M, so we will get Cm, EL is Em minus Ek naught, right, is equal to, on the right hand side, I have psi m naught, H prime acting on psi k naught is what is left here, right, minus Ek. So we should have got Ek1 of psi m naught psi k naught. Obviously this will be 0 because the summation is for L not equal to K, right? So this goes to 0. So finally Cm is the coefficient of terms which comes, right? CL Cm is all the same. So Cm is given by this expression. Once again, I think you will remember what this bracket means. But here the bracket is divided by Em minus Ek naught. So what we mean is, in the Fourier expansion of psi k prime, let's say Cm psi m naught. This is what the perturbed wave vector is, right? It's some Fourier summation of Cm's. So what it means is, let's say I have an electron with wave vector k. After being incident to this perturbing potential, it got scattered to k prime. Okay, the Cm's tell you what is the probable direction in which it gets maximum. If Cm value is high, then it means that there is a maximum probability for k vector to be scattered along this Cm direction. along the psi m direction. If Cm value is low, then the probability to scatter along this is low, right? So the probability that the wave gets scattered along k direction is proportional to Ck dash. I mean Ck square, Ck mod Ck square. Okay. Now that we found the wave vector, so the total wave vector is written like this. If we compare this expression with our previous drawing, what we are saying is these wave vectors. So these were all unperturbed. These are all unperturbed wave vectors, right? The point we are trying to make is the perturbed wave vector, okay, psi k, it depends upon the overlap of that particular unperturbed wave vector with all the wave vectors with which it is interacting. For what we mean is, let's say here, let's talk about this wave vector here, okay? And if this wave vector interacts with any other wave vector, okay, the strength of that interaction will determine how this wave vector will change. And the summation of all these things is what is this final wave vector solution. Right? So basically we can see it from here. The Ck is being scattered from k to k dash. How far it gets scattered depends upon the strength of these interactions. Okay. Now that we calculated the first order energy, you can also calculate the second order energy by perturbation theory. We go back to our previous expression here. So this is the second order expression. We put back the second order expression. And now, as we did previously, we have to do multiply from the left hand side with psi k naught, both sides. Here also you do psi k naught both sides. What we will get is ek2 is the overlap of this potential, right? So whatever the potential that, let's say as I drew it previously, this is the unperturbed let's say wave vectors in an infinite potential well. The changes in the second order changes in energy of any level, okay, it depends upon now the overlap integrals. Now the bracket comes into picture. Like it tells us that these energy levels changes depending upon the interaction of this wave vector with other levels, right? And this interaction has maximum strength when the levels are close by. You see, they are divided by the separation. So what we mean is, if I have two levels which are close by, let's say this is first level and I have the second level. If the two levels are close by, then it has maximum impact. If the levels are farther apart, then they have little impact on each other. Moreover, if let's say I have this electron, this level, right? If it interacts with an energy level lower than its level, the post perturbation energy increases. And if they have an energy level which is low and it interacts with an energy level which is high, so post perturbed energy level now reduces, right? So what we are trying to come at under these situations is, if I have, let us say, two atoms with energy levels like this, right? And I bring these two atoms close by. What this perturbation energy tells you, right? If we have two wave vectors which are very close in energy, right? And if they interact with each other, the energy level which is slightly higher than the other one goes up, and the energy level which is slightly lower than this one goes down. And this interaction, how much it goes up and how much it goes down, depends upon how close these energy levels are. The closer they are to each other, the maximum force with which they repel each other. This energy level, which is at this energy, rarely talks with the energy level which is much higher because the separation is larger. So the denominator gets higher and the entire perturbation now drops. Right? So the other high lying energy states do not really contribute to changes in energy of this level. Right? I hope things are a little bit clear now. Now let's get back to what we intended to solve. Okay, so now we had some basic about the perturbation theory. We determined how do we find the first order correction in energy. So let's say here we saw what is the first order correction in energy. We saw how do we get the first order correction in the wave vector, right? And we saw the second order correction in energy. The second order correction in wave vectors is to be much more complicated, so we are not going there. So we will stop here to tell you that if we have two levels which are interacting, the interaction strength is maximum if the levels have similar energies, and the level which interacts with the energy level which is lower gets pushed higher further, and the one which is lower gets pushed lower further, right? So now the interaction now stops, right? So there is some kind of a feedback loop, right? For what I'm trying to say is, let's say I have energy level here and I have another one here, right? If the interaction brings them closer, let's say, okay, then you can see that they will get the interaction energy will just blow, right? Because they are getting now closer and closer, and the interaction now will get stronger and stronger, so they will just blow. What actually happens in physical systems, and which makes intuitive sense as well, if these two states interact, their energy levels get separated. As the energy levels get separated, their interaction strength also drops, so they will stabilize at some point, right? So this guy goes up and this guy comes down, so finally they will settle down at this, having some difference in energy between these two which interact. Okay, so what we saw is, let us take, so now, okay, now that we understood how the perturbation works and such, let's see that we have an electron which is incident in a periodic potential, has a wave vector k, and now we assume that these potentials are small such that it just perturbs the free electron wave vector. We do not assume that there is going to be a large change either in the energy of these electrons nor its wave vector, right? So it is going to be mildly perturbed. And this is a periodic potential, so we write it V of R plus capital R. Capital R is the lattice periodicity, is equal to V of R. And because it's periodic, you can also write its Fourier expansion like this, right? This is something that we have previously seen. The probability that the electron gets scattered along K prime in a different whatever, like we have an incident electron at K, what is the probability that it gets scattered along K prime is this overlap integral, right? You remember we saw this overlap integral here. Psi K1 is the probability of let's say psi K1 is the modification in the current wavelength. So this is K, right? We add psi K1 and bring it to this point, right? And we bring it closer and closer to this particular value. So how do we find this? We find it Cm. So the direction, the probability for the electron to be scattered along this m direction depends upon this overlap integral. And this is what we do here. So finally, we take the electron wave vector and then we convolute it. We make the potential act on this and then does the overlap with psi k prime. Right? So now we have to explain. So this is what is called as the scattering matrix element M. It is just Cm. So the magnitude of Cm is what is a scattering matrix element. It is basically this overlap integral. Right? So now let's calculate this. I write this as m k prime because it is the probability for it to get scattered from k to k prime. And we write psi k's as the normal unperturbed ones as plane waves, e power ikx, ikr, right? So psi k is e power ikr, and we write from the periodic, the Fourier expansion, psi sigma g vg e power ig dot r, right? and psi star is e power minus I k dot r. It's easy to see that the summation now can go out. So we have the summation outside. We bring the integral inside the summation. We have e power minus I k prime r e power I g dot r into e power I k dot r, right? So this can be written as summation over g integral e power I k prime minus k prime plus g plus k, right, dot r into vg dr. And it's easy to see this is minus infinity to infinity. This integral will hold a non-zero value. So basically this is delta of g plus k minus k prime, right? So basically this will the entire integral will have a non-zero value which is be equal to vg only if k plus g is equal to k prime. What we mean is g is a reciprocal lattice vector, right? So this is g and this is k and this is k prime, right? So what we mean is the scattered wave vector should be a summation of the incident wave vector plus the lattice constant. Another way to see it is, let's say that you have a lattice like this and I have an electron which is incident whose wave vector looks like this. The k prime, which is the scattered wave vector, should be a summation of the incident with any of the lattice constants, right? So it can be what I show here. It can be this one. This can be a scattered wave vector. This can be a scattered wave vector. What cannot be a scattered wave vector is here, which does not belong to any of the reciprocal lattice vectors. Right? This is not G. So this cannot be K prime. Right? So what we mean is you have a non-zero scattering matrix element only if the scattered wave vector is a summation of the incident wave vector plus a lattice constant. This is what our our perturbation theory of a periodic potential tells us. From the perturbation theory, we came to the solution. We came to this idea that the scattering matrix element has to do with the overlap integral, right? We take the overlap integral and then substitute the potential to be a periodic potential. What comes out is that the scattered wave vector should be a summation of the incident wave vector plus the reciprocal lattice vector. This is the only way in which the scattering matrix element will have a non-zero value. Right? But it is not just that, right? So the coefficient of the scattered, let's say the Fourier series, coefficient of the Fourier series term in the scattered wave vector Cm, that's what we saw previously, depends upon the overlap integral as well as the separation in energy, right? So basically what we are trying to say is these energies are still free electron energies. So it is h bar square k square by 2m. So basically the mod k should be same or almost similar to k square, k dash, in the sense that the scattered wave vector and the incident wave vector should not largely differ. So k plus g, this is the condition that we saw from the scattering condition, and this should be the condition in which you have maximum scattering probability, right? If we put these two together, the only condition in which will satisfy both of them is the incident k is plus or minus g by 2. G by 2 is G is the reciprocal lattice vector and G by 2 is half the reciprocal lattice vector. So what we mean is an electron which is incident on a lattice gets diffracted, gets scattered only when its k vector k is closer to half the reciprocal lattice vector. Only then it gets scattered, otherwise it just goes unperturbed. It can be seen from here, right? So let us take some k value which is much smaller than what we are talking, right? much smaller than half the reciprocal. So let's say this is the reciprocal lattice vector, that is 2 pi by a. Let's take some value. This is pi by L, right? This is 2 pi by L. Okay. So let's say this is the first k value which is allowed. And we saw that it can be scattered only when you add to this another reciprocal lattice vector, right? If you add plus to this point, you add, let's say, G, this is G. It takes you to this particular point, which is much higher in energy, right? So basically, this K and this K dash can rarely happen. Or even if you add to the negative side, you get something like this. This to be K prime, which will rarely happen, right? While what has the maximum probability is you have an electron here whose K is G by 2. Right? Now this guy can be scattered diagonally opposite, right? Any point here, or it can be scattered in any of these circumference values. Oops. All of these guys will give you G. This is K prime. This is also G, right? So any of these things will give you a G. So the maximum probability of, an electron whose K value is close to half the reciprocal lattice vector has the maximum probability to be scattered by the lattice potential, right? So basically this line, which is also the Brillouin zone, first Brillouin zone edge, right? How we take Brillouin zone is take the reciprocal lattice vector and divide it by 2. That's how we make the first Brillouin zone or the Wigner-Seitz lattice, right? So this is where is the origin. This is the line of the Wigner-Seitz lattice or the first Brillouin zone. And electrons which are close to this have the maximum probability to be scattered back, right? So a wave which is K plus or minus pi by a gets Bragg reflected. It is called Bragg reflected because from here you can get to the condition for Bragg reflection that you see in X-rays and such. We don't have to go there now, but then it is called Bragg reflection, right? So what we mean is an electron which has K equal to plus or minus pi by a. So let's say an electron here gets scattered back in the exact opposite direction, right? It reaches this boundary, gets again scattered back, again gets scattered back, right? So it keeps getting scattered, and hence it forms what is called as a standing wave. This leads to a standing wave pattern because you have a summation of e power ikx by a plus e power minus ikx by a. There are two possible solutions. One is psi plus, another one is psi minus. So basically you have two standing wave solutions for an electron whose K vector is close to the Brillouin zone edge. Right? For an electron here, the only possible, you don't have any traveling wave solution, but you have only a standing wave solution because it gets scattered Bragg reflected at the zone boundaries. Right? So now you have two solutions. The psi plus solution where you have electron accumulation. So basically this is mod psi square, right? So basically this is the probability of finding an electron. An electron bunching close to the ion core, this is called as an S wave solution. A solution where the electrons are pushed away from the ion core but at the center of the separation, this is called as a P wave solution. So you have two standing wave solutions, and these standing wave solutions have largely differing energy values. How do we find the potential energy of these standing waves? We take these waves and then we act on it with the potential operator, right? We get the expectation value of the energy, and the potential is a periodic potential. You can write the periodic potential in this form: Ug cos 2 pi x by a. Of course, this is period. It has a periodicity of the lattice constant K. And we use this as an operator and then work and then find the difference in energy level between the minus state and the plus state, we get the Fourier constant Ug. So what it means is the gap in the energy between these two states is the magnitude of the potential of the lattice. So what we mean is these two standing waves are a result of something whose k is 2 pi by a, right? Whose k value is, sorry, not 2 pi, k value is pi by a, half the reciprocal lattice constant, right? And this k can get scattered to k prime via a reciprocal lattice g, right? And the separation between these two waves, the energy separation between these two waves, this is E psi minus and this is E psi plus, is basically Ug, the Fourier component of the periodicity of this one, right? So because this is V, is written as Ug cos 2 pi x by a. Ug is the amplitude, right? So it is the amplitude of the potential is what is the energy separation between these two states. So we have proved a few things. We have proved the existence of a band gap between two states, right? We showed that when you have k values closer to the Brillouin zone edge, the energy levels separate. You have two distinct energy levels and nothing in between. And the separation energy level is proportional to the coefficient of the Fourier series of the lattice potential, Ug. The same thing could be approached in in a different method called as the Crony-Penning model. This is something that you must have seen in E614 as well as in any other course that you have previously seen, right? So basically, if we take a potential like this and do the same thing that we have done before, solve the Schrodinger equation in this region, solve the Schrodinger equation in this region, and then look for the boundary conditions, right? For instance, here the Schrodinger equation, let's say 1 is with E equal to 0 is written as A e power I kx. Psi 2 is with the potential V. I think I have noted it wrongly. This is psi 1, this is psi 2. Okay. Then you get two equations. This is an equation for the wave vector here, big equation for wave vector 2. And if you assume that both the wave function and its derivative are continuous, you get two equations. But then we have four unknowns here, A, B, C, D, right? But what we do is, because of the periodicity of the this one, you can also say that the same wave function exists here as well, right? Because whatever that you have here should be same here as well. So you can have two more equations here. You have two equations here, you have two equations here. Finally, you have four equations, four unknowns, and you can solve for it. When we solve for this, this will be a detailed problem, will be your homework. You have seen this in many places, so it's better that you do this. What we do, what we get is, we get this kind of an equation as a solution for K. And it's easy to see that the left-hand side is a cos something, right? And hence it can have only values between -1 and 1. And the right-hand side can have probably many values. So only when the right-hand side values have, let's say here, all these regions are regions in which there are no solution. So you have only in certain, let's say here, like here, right? And here to here, only in certain alpha A values, you have a realizable solution. You have values for which K exists reasonably, right? And even this is an evidence to show that there will be certain energy levels which are not allowed in a traditional semiconductor. So if we draw the free electron wave vector solution as like this, which is a parabola which extends, right? And we saw just now that for wave vectors very close to the zone boundary, you start to have standing waves, and hence the solutions start to deviate from the free vector or the free electron dispersion, and then start to give this sort of a dispersion, right? So it starts to bend down so that the energy value is close here, right? So here also you will get something like this. You will get a discontinuous energy profile at these points where you start to have standing waves. So these are, sorry. So these are standing waves. Wave solutions. This will be, let's say, modulus psi minus square. This will be the energy of modulus psi plus square. And this separation is UG, right? And obviously we also we previously saw that you can have many allowed states. Each one of them is 2 pi by n. The smallest k value should be 2 pi by n. And if I have, let us say, n unit cells, I should fill up all the available states, right? So basically I have n available states in the first Brillouin zone. Minus pi by a to plus pi by a will give you n states. And each can fill 2n number of electrons. Right? So if I have a unit cell with one atom with one electron, then the first band, let's say this is the first band, gets only half filled, right? If I have a unit cell with one atom and two free electrons, then it's easy to see that the first Brillouin zone gets completely filled, or the first band gets completely filled, and you have energy levels below which everything is filled, and you have no density, or there are no energy levels above it. So this is the origin of having materials which have a metallic behavior and materials which have an insulating behavior, right? So this, whatever the solution that we clearly maybe right now saw, is what is called as a nearly free electron model. It is based on a few assumptions. We assume that the electrons are nearly free, and we talked about wave vectors or wave functions which are modified plane waves. So what it means is, if I assume periodic lattice, the potentials which look like this, right? Typical potentials look like this. The electron wave vectors we're talking do not exist here below in the atomic potentials, but then they exist here. So it is only with E greater than V you have what is called as the scattering behavior, right? So if you remember our previous lectures, so these solutions are almost plane wave solutions, and it is under these situations in which we are currently seen. If we talk about electrons which are below this potential, we talk about bound states and such, then we start having difficulties with this particular treatment. And then we go into atomic orbitals and such, and we talk about linear combination of atomic orbitals and something. Those are the topic of discussions from the next lecture. Okay, so we will stop here now, and next time we meet, let's talk about linear combination of atomic orbitals and tight binding model and such. Okay, thank you.